In our group, we use the tools of quantum mechanics and statistical mechanics to solve problems related to energy and improving the quality of people's lives. We aim to separate CO2, or carbon dioxide, from the atmosphere or from flue gas, and we do that by developing computer models of adsorption and diffusion through nanoporous materials. The way we generate energy is by burning fossil fuels for the most part, and we're going to continue to do that for the next probably 20 to 50 years because that's the available source of energy that we have. So the Center for Simulation and Modeling is a new effort launched by the university, recognizing the need not only to use high-performance computing, but to have expertise in high-performance computing. And so the Center for Simulation Modeling is to help researchers, students, postdocs, be able to utilize the power of multi-processor computing. Well, we're trying to solve problems related to separating things. In many instances, we've got mixtures of things that we want to take apart into their components. One example is capturing CO2. That's separating CO2 from a mixture of gases. So one of the projects we have uses molecular modeling to study how carbon dioxide interacts with what we call nanoporous materials. These are materials that have extremely small pores or holes in them. And what we want to do is design the right material so that carbon dioxide will go into this material selectively, and thus we'll be able to capture that CO2 and keep it from going into the atmosphere. So I have a little model here, a model of a carbon nanotube. So in this model, these black things, these represent carbon atoms. If this were the actual size, it would be less than 1/1000th of a meter in diameter. Carbon nanotube has very, very high strength, higher strength than steel on a per weight basis. One of the challenges is you'd like to be able to do very accurate calculations on very large systems. Currently, there's no way of simulating a system of, say, 1,000 atoms with very, very high accuracy. You could have hundreds of thousands of materials from which to choose. It's infeasible to do experiments on every one of those. So what we try to do is guide experimental efforts by honing in on those materials that are most promising. Then we hand those off to the experimental colleagues. They make them, synthesize them, and test them. What we're hoping to find is a material that will selectively absorb CO2 and do so with a low energy barrier, so it happens very rapidly, and with a low energy cost. Basic research is important because nobody can predict the future. You can never tell where something that looks like completely basic and not applied to anything, how it will crop up. When lasers were first developed, nobody could think of a single instance where they would be useful to anybody. And yet, we can't go through a single day without using a laser, whether it's in your computer or whether the policeman's measuring your speed with a laser or whether you're playing a compact disc. Our research is carried out on the computer, writing computer codes or using computer codes to develop mathematical models that then can tell us answers, tell us how things interact. One simulation could take a few hours or a few months of CPU time, depending on the level of accuracy and the kind of question you're asking. We then run that code on supercomputers or on high-performance computers. And so that happens at various locations. Here in the Center for Simulation and Modeling, Pittsburgh Supercomputer Center, and other locations. We've had some great collaborations with the National Energy Technology Laboratory right here close by to the campus. I also have collaborations with people at Penn State, University of Virginia, Virginia Tech, and other places. It's a lot of fun working with younger people who are excited about science and want to contribute. It's especially fun to see a graduate student progress from being dependent and uncertain about what they're doing to the point where they're now leading and driving the research. They're coming with ideas, they're coming with new insights. Then I know they're ready to graduate and they're really PhD material. My dream would be to predict materials, then get them synthesized, and then watch them go into actual usage and watch them being utilized in processes that affect people's lives.